Consider a rod of uniform thermal conductivity whose one end x is equal to 0 is insulated and the other end x is equal to L is exposed to flow of air at temperature T infinite with convective heat transfer coefficient H. The cylindrical surface of the rod is insulated so that the heat transfer is strictly along the axis of the rod. The rate of internal heat generation per unit volume inside the rod is given as Q dot is equal to cos 2 pi x by L. The steady state temperature at the mid location of the rod is given as TA. What will be the temperature at the same location if the convective heat transfer coefficient increases to 2H? This is an interesting question from heat transfer. Let's look at the solution. We are given with a rod whose one end at x is equal to 0 is insulated and the other end x is equal to L is exposed to an airflow of temperature T infinite. We also know that the heat transfer is strictly along the axis of the rod. From the image, it is clear that the axis of the rod is along x-axis. We are also given that the rate of internal heat generation per unit volume is Q dot is equal to cos of 2 pi x by L. Also, from the basics of heat transfer, we know that for a steady state one-dimensional heat flow with non-uniform heat generation, the governing equation is d square T by dx square plus Q dot by K is equal to 0. Sending Q dot by K to the right hand side will give us d square T by dx square is equal to minus Q dot by K. Integrating this equation on both sides, that is integral d square T by dx square is equal to integral minus Q dot by K into dx. Substituting Q dot is equal to cos of 2 pi x by L in the right hand side of the integral equation, we get dt by dx is equal to minus 1 by K into integral cos 2 pi x by L dx plus a constant C1. This is the figure we were considering to solve this question. So, integrating the above equation, we get dt by dx is equal to minus 1 by K into L by 2 pi sin 2 pi x by L plus C1. Let us consider this as equation number 1. As per the given boundary condition at x is equal to 0, heat transfer due to conduction is equal to 0 because the end at x is equal to 0 is insulated. That gives us dt by dx is equal to 0 and that gives us constant C1 to be 0. Now, integrating the above equation number 1 again on both sides, we get temperature T is equal to L square by 4 pi square K cos 2 pi x by L plus C2. Now, the other boundary condition is that at x is equal to L of the rod, heat transfer due to conduction should be equal to heat transfer due to convection. That is, the basic governing equations say that heat transfer due to conduction is minus Ka into dt by dx at x is equal to L, and the governing equation of heat transfer due to convection says that H into A into temperature at x is equal to L minus T infinite. Substituting T is equal to L square by 4 pi square K into cos 2 pi x by L plus C2 in this equation and simplifying, we get that temperature at x is equal to L is equal to T infinite. That implies L square by 4 pi square K cos 2 pi L by L plus C2 is equal to T infinite. This turns out that T infinite is equal to L square by 4 pi square K plus C2. From this equation, it is clear that constant C2 is not a function of convective heat transfer coefficient. That implies temperature T is a function of cylinder axis only, but not convective heat transfer coefficient H. Therefore, TA remains same even if H becomes 2H. The correct answer to this question is option C.